Hello, students. We are talking about 5.3, which is proving triangles congruent using side, 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 and side angle side. So up to this point, we have had to prove all three sets of angles and all three sets of sides congruent to prove that the triangles are congruent. But I kind of alluded to the fact that that is not always the case. So you can prove triangles congruent with far less information. So true triangles can be congruent by all 6 pairs of things, but it's possible using fewer pairs. So if two triangles have the same 3 side lengths, then there is a series of rigid motions that will show the two triangles are congruent. This leads to this postulate that is below. So it's the side, side, side congruence postulate. If 3 sides of one triangle are congruent to 3 sides of a second triangle, then the triangles are congruent. Now, for the purpose of what we are going to do, you are going to use SSS for your reason and a proof. What you need to understand is all this does is it proves triangles are congruent. So make sure you use this at the right time. And you have to have stated that a set of sides is congruent, a set of sides is congruent, a set of sides is congruent in order to state that the triangles are congruent using this reason. Okay, so that's side, side, side is the idea. Okay, so true or false, we're going to justify it. If the congruent sides in one isosceles triangle have the same measure as the congruent sides in another isosceles triangle, then the triangles are congruent. So I always like to pause and think about that for a second. If you need to think longer, feel free to pause this. But the idea is this, is that if I make this the length of my side of my isosceles triangle, so those two are the same, is there any way for me to make this triangle different with those same side lengths? And the answer is yes. Is essentially if you think about taking this side length here and just opening it up, use that same side length for the other side, your base becomes different and you have two not congruent triangles. Okay, so this is not a true statement, and there's a justification. All you have to have is one counterexample to prove that it's not true. Okay, so triangle ABC has vertices. So we have A at 1, 1, and anytime that I graph something, I'm going to label it. B is at 0, 3, and C is at 2, 5. So we have our triangle ABC that's there that we're going to graph. And some of us need to keep working on making sure that we label everything. Triangle EFG has vertices, and it gives us those. So at 1, negative 1 is E. F is at 2, negative 5. And G is at 4, negative 4. And there's that triangle, not the greatest drawing, but it's still there. And it's asking, is triangle ABC congruent to EFG? So it's in that order. You have to be really careful. So they're asking, is AB congruent to, so AB first 2 letters here, EF first 2 letters there. So it would be EF in this case. Is BC congruent to FG, so BC would have to be congruent to FG that's in there, and so on and so forth is what we're kind of looking at in this case. I'm doing a quick check over of this one. Okay, so find the side lengths of each triangle here. So side length AB, if I'm doing that, I'm going to find my right triangle. It's a 1 by 2, so I'm doing 1 squared plus 2 squared, 1 plus 4, which is 5, and this is the square root of 5. And I'm just going to leave it as a square root because it really the only reason I'm finding these is to see if they're equal to each other. So I found AB, and then I'm going to look at EF next. So EF is a 1 by 4. So we've got that 1 by 4 here, 1 squared plus 4 squared. So 1 plus 16 or 17. And then you would take, remember, equal to C squared. So you would take a square root of it. So it's the square, oh, not that one. EF is the square root of 17. Now I'm thinking at this point, I can stop and continue on. So are they congruent? The answer in this case would be no, that they're not congruent. And we can utilize, they've got a few different reasons in here. So we can utilize the fact that AC, okay, they've got AC, they've got FG. So I guess I need to solve a little bit more. I need to solve for FG. So FG is a 1 by 2, which is the square root of 5. I actually found that earlier with my AB. And we want to know, is FG not congruent to AC? So which one do we want that to match up with? We want FG to match up with, I got to go up to my congruent statement. FG should match up with BC. So we want to match it up with BC. BC is 2 by 2. So we would do 2 squared plus 2 squared, which would be 4 plus 4 or 8, and take the square root of that. And so that's BC, so that's the square root of 8. And since FG is not equal to BC, that's why it's a no. So make sure that you match up the correct pieces. Just because AC is not equal to FG doesn't matter, because those are not the sides that we want to match up. And otherwise, we want all the corresponding pieces to match up in that case. Okay, so that's that answer. Okay, another think about it here on the side of that paper. Both legs of one right triangle are congruent to the legs of another right triangle. Are the triangles congruent? Okay, so let's think real quick here. We have a right triangle, and it's saying that in this right triangle, call this A, that it's saying that both of the legs are congruent. So we have a right triangle. We know the right angle, okay? And so we have a leg and a leg, not the hypotenuse, and a leg that's congruent to another leg. If that's the case, is that enough to know? And the answer in this case is going to be yes, because when you're solving this, you are going to do, let's say this is x and this is y. You're going to do x squared plus y squared equal to that distance squared on that other side, and you're going to solve for that d that's over there. Well, if this is x, then this is also x, and this is also y, and so that exact same setup is going to be over here, and so this piece is also going to be d. And so in that case, we have side, side, side congruence that gets us there. Now, we follow that up right away with the idea of proving triangles congruent through side angle side, because what you see here is a side angle side example that works. Now, that's a special case because we can find that third side. But the interior angle formed by two adjacent sides of a triangle is called the included angle. Now, this is a big idea for side angle side, understanding this is not angle side side or side side angle. This is the angle is between the two sides that you know are congruent. So if two triangles are formed using the same side lengths and included angle measure, then there is a series of rigid motions that will map them onto each other, which leads to the SAS congruence postulate. Again, a reminder, SAS proves triangles congruent. So you have to have three statements prior to this that say that you have a set of sides, a set of angles, and a set of sides that are congruent. And in the diagram, you have to be able to see that that angle is included between those two sides. So what do I mean by that? Well, if I have a triangle here, I'm going to call this ABC, and I know that side AB is congruent to a side in another triangle and side AC is congruent to a side in another triangle, then there are three angles that exist in this triangle. Okay, so if that's listed congruent, that's listed congruent. I have the two side parts of this, but I don't have the A part of this. Okay, and if this is not a right triangle, I don't have a way to find BC. Okay, but if we are given angle B, notice that angle B there is not between those two given sides, okay? It's not that if I take the two given sides and trace over them, they make up angle A that's right there. So it is important that you talk about the included angle when you talk about side angle side. Okay, so giving an example with this one, we've got a kite example here. So the kites shown appear to be made of congruent triangles. If DE is congruent to FE, so we're going to mark it. We mark our diagrams a lot. And EG bisects angle DEF. So understand what this says. It's saying that segment EG splits in half. That's what bisects means. So splits in half angle DEF. Now, a lot of students struggle with this idea, but what is split in half? The DEF is split in half. So angle DEF is split in half by EG. That means that we have a set of angles that are congruent. And that is by the definition of an angle bisector that's there. And we're trying to prove that DEG is congruent to FEG. So here's our two-column proof. I just kind of gave away some of it, but that's what we're going to have here. So we have a given statement, just simply that DE is congruent to FE. Make sure you watch your notation and you're using correct notation. Now, I'm going to on the side over here, so we've stated this given statement, but on the side over here, I'm going to put a little S. Now, the reason I'm doing that is that represents that I have now stated a set of sides in the triangle that are congruent to each other. So I'm going to mark that. Then I state EG bisects angle DEF, which is also a given statement, so I've mentioned my given here. Okay, now that, since it's not a congruent statement, should lead me to saying something that's congruent. And that's what I just talked about up here, these angles. So we know that angle DEG is congruent to angle FEG based on that information. And that's the definition of an angle bisector, or the definition of a bisector. Okay, so I used step 2 to state step 3, and I'm going to put an A out here in front because that tells me that I have a pair of angles in my diagram that should be marked. Okay, the next thing is a blank, and so this is where we have to understand our proofs. we think about our proofs. We have our givens. We've used both of those, and we've stated things from our givens. You have the diagram that you can utilize. Okay, so if I look at the diagram, there's two main things you're going to look for in a diagram, and that's going to be you're looking for vertical angles or you're looking for reflexive property. Okay, and in this case, hopefully, as soon as I say that, it comes to mind, but we have reflexive property here right now. So EG is congruent to EG is my statement here. So I'm going to say segment EG is congruent to segment EG by the reflexive property. Again, that can come from the diagram. Okay, and I'm going to put a little S over here. Now, the reason I did that is because notice I checked this step off because that led me to step 3. And now I have an S, an A, and an S. And I can go to my triangles being congruent because now I have 3 statements with pieces that are congruent, so parts of a triangle that are congruent. Those happen to be 2 sides and the included angle. So if we think about these sides over here, side over here, that angle we're talking about is included between them. So we have side angle side that allows us to state that these triangles are congruent. You can only use this if you've already made the 3 statements. And remember, you're using this to say that triangles are congruent. Okay, that's what we have for today.